Writing equations for exponential functions. So let's review the basic layout of an exponential equation. So we have f of x equals ab to the x power. So the a is the initial value. That's your beginning, your start, how much of something are you starting with. Then we have the b, that is your growth or decay rate. So if you're increasing at a certain rate, it's growth. If you're decreasing at a certain rate, it is decay. So remember, y, that is your dependent variable. And x is your independent. Usually time for these. So to write an equation, you need two pieces. You need an initial value. This is your a. Okay, this is the starting, this is the beginning value for the function. For tables and such, it's where your x is equal to 0. On graphs, we call it the y-intercept. Then you also need that growth or decay rate, and that's your b. So the value for which y is increasing or decreasing between consecutive x values. How quickly are you increasing or decreasing on your y's? Then also remember that x is the exponent for these equations. So let's start with some tables. So example 1, write the exponential function that is represented in the table below. So first we're going to decide, first of all, is this growth or decay? So just kind of like linear, we're going to decide how do I get from one value to the next on my y's. So if we look at from 1 to 2, I could add 1, but then if you do 2 to 4 and you try to add 1 again, it's not the same. So adding is not going to work. Now to get from 1 to 2, I can also multiply by 2. And then if I keep looking down my table, 2 to 4 multiplies by 2. 2 times 2 makes 4. 4 to 8, 4 times 2 makes 8. 8 to 16, 8 times 2 makes 16. So for exponential functions, you're multiplying on the y values every time. So this times 2, that's your b. That's that growth or decay rate. So in this case, because 2 is larger than 1, that means this is a growth. The growth or decay rate itself, that's your b value. B is equal to a 2. The last part we need for an equation is the initial value. So remember, this is where x is equal to 0. This is like the y-intercept. So I find x is 0, look for my y value. So in this case, a is a 1. Your initial value is a equals 1. The last thing is to write the equation. So the layout, y equals a times b to the x power. Well, we said that the a was a 1 times b was a 2 to the x. Now, because a is a 1, 1 times anything is still itself, so in this case, we can simply write y equals 2 to the x. The 1 is understood in the front. You don't need to write it for this one. Example 2. Write the exponential function that is represented in the table below. So I have, now my y values are decreasing top to bottom. I don't know about you, but 256 down to 64 is something that doesn't come easily to me. But I can do 4 to 1. That is something that's a little simpler. So 4 to 1, you can think of this as subtracting. I can subtract 3, but if you look at 16 to a 4, subtracting 3 is not going to work anymore. Instead, though, I can take 4 and divide it by 4 to get a 1. Now here's our problem. Our layout is a times b to the x. There's no division in this. So we have to think of dividing by 4 as being multiplying by 1/4. So you can't use division, you have to use multiplication. So if your rate is dividing by a number, that's really multiplying by that number's fraction, 1 over whatever it is. So 16 to 4, if I multiply 16 by 1/4, you get a 4. 64 to 16, again, times it by a 4th. 256 to 64 is timesing by a 4th. So in this case, b is equal to 1/4. So since B is 1/4 and 1/4 is smaller than 1, that means this table actually represents decay. The growth or decay rate is B equals 1/4. Now we have to find that initial value. So the initial value, again, that is where x is equal to 0. This is the y-intercept. So look at your table, 0 to 56. So 256 is the A value. Now that you have both pieces, we need to substitute them into our layout. So we have y equals A, which is 256, times B, which is 1/4, to the x. Write the exponential function that is represented in the table below. So again, we see our numbers are decreasing, 216, 36, 6, 1, 1/6. So trying to get from 216 to 36 is not easiest. So 6 to 1, I know that that's going to be multiplying by 1/6. Since we're decreasing, you're going to have a fraction. And again, 1 times 1/6 does in fact equal 1/6. So that works there too. 36 times 1/6 is equal to a 6. 216 times 1/6 is equal to 36. So B, for example 3, is 1/6. So for this example, since B is 1/6 and 1/6 is smaller than 1, we have another decay. Now the growth or decay rate, that is the B value. So in this case, it is 1/6. That's how we're changing every time. So now we need to find the initial value. So the initial value is where x is equal to 0. If we look at our table though, I have x equals 1. So I need to get to my 0. Well, to get to 0 on the x, I'm going to have to work backwards. So on my x's, if you see, you're adding 1 every time on the x's. So going backwards means I'm going to have to subtract 1. So 1 minus 1 makes my 0 that I'm looking for. Same thing on the y's, I'm going to have to work backwards. So multiplying by 1/6 down the table means going backwards on the table, you're going to have to multiply by 6, the reciprocal of the fraction. So 216 times 6 gives me 1,296. So my A value for this example is 1,296. A equals 1,296. Now that we have both our pieces, we need to substitute them into our general layout. So we have y equals A, 1,296, times 1/6 to the x. Here's our A, here's our B. Now let's talk about some word problems. So example 4, the figures below are stages of the Sierpinski triangle. In stage 0, there is one black triangle. In each subsequent stage, a white triangle is added to the center of each black triangle, dividing that triangle into 3 black triangles and 1 white triangle. The number of black triangles increases by a factor of 3 in each stage. And so we see a picture of how that works here. Stage 0 is 1. Stage 1 has 1 white and 3 blacks. Stage 2 has 1, 2, 3, 4 white triangles and 1, 2, 3, 4, 5, 6, 7, 8, 9 black ones, and so on. So letter A says, write an exponential function, f of x equals ab to the x, to describe the situation where x is the stage number and f of x is the number of black triangles. So when you have a pattern like this, step 1 is always to create a table. Tables are easier to work with. So we're going to create a table, x and y. So it said that x is the stage number. So if we just use the stages we're given, that means I have stage 0, stage 1, stage 2, stage 3, and stage 4. Then it says f of x, or in our case y, is the number of black triangles. So for stage 0, there was 1 black triangle. Stage 1, we had 1, 2, 3 black triangles. Stage 2, we had 1, 2, 3, 4, 5, 6, 7, 8, 9 black triangles. Stage 3, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 2, 3, 4, 5, 6, 27 black triangles. Now, stage 4 is not the easiest to count. So we're going to use the stages that we have in 0, 1, 2, 3, because the pattern should continue for 4 and on. So just like the front, we need 2 pieces. We need our initial and we need our rate. So the initial is where x is equal to 0, which we do have. So a is 1. Our rate is how we are changing. So to get from 1 to 3, you multiply by 3. 3 to 9 is multiplying by 3. 9 to 27 is also multiplying by 3. So our b is equal to 3. So to write this equation then, that's step 2. We need y equals ab to the x. Well, a was a 1, b is 3 to the x. Now, since your a is a 1, we don't need it because 1 times anything is itself, so our final equation is just y equals 3 to the x. So this equation gives any number of black triangles for any stage. So I could use stage 32 here for x and do 3 to the 32nd, and that'll tell me how many black triangles is in that stage of the pattern. That's why this is useful, because trying to continue this pattern here is not easy to do drawing it out, especially as the triangles get smaller and smaller. Example 5. Suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles each week. Write an exponential function that best describes this situation. Be sure to define your variables. So first, I need to figure out what my two variables represent. So we have x and we have y. So x is the independent, and it's usually time. So we see that something says it doubles each week. So that means x is going to be the number of weeks they're watching this beetle population. So, well, y is the number of beetles. That's what they're trying to figure out. So it says write an exponential function. Well, that means my layout equals y equals ab to the x because it's exponential. So I need my two pieces. I need my initial and I need my rate. Those are the two pieces that we need. The initial is the a, the rate is your b. So to find the initial, you're finding how many beetles did you start with in this little experiment. So it says suppose 30 flower beetles are left undisturbed. That is the initial. So a will be equal to 30. The rate is how quickly these are increasing or decreasing. So it says the beetle population doubles each week. So every week I get twice as many beetles in my bin. So my b is going to be a 2. If it was triples, that's times 3. If it would say halved, that's times 1/2. That'd be a decreasing situation. So now that we have the a and the b, we're going to substitute them where they go. So a is the 30 times b, which is the 2, to the x. So just like the pattern, this is useful for telling me how many beetles would be in this warehouse bin after x many of weeks. So I could figure out x is, let's say, 52. That could be a year. How many beetles would be in there? Example 6. There are 20,000 owls in the wild. Every decade, the number of owls decreases by half. Write an exponential function to represent this situation. Be sure to define our variables. So again, I need to show what x and y are representing. So x is the independent, that's your time. So it says every decade. So a decade is 10 years. So number of decades. Then y, well, what's happening every decade? The number of owls are decreasing. So in this case, y would be the number of owls. So it says write an exponential function. So that means we're going to have y equals a b to the x. So again, a is your initial and b is our rate of decline or increase. So if we read our situation, it says there are 20,000 owls in the wild. That's our starting. So a is equal to 20,000. Then it says our rate, what's happening to these owls, the number of owls decreases by half every decade. So our b is 1/2 this time. So this is an exponential decay because these owls are decreasing in number, not increasing. So when we write our equation, y equals a, which is 20,000, times 1/2 to the x. So the number of owls is going to be 20,000 times 1/2 raised to the number of decades we're doing this for.